for inviting to ITAMP workshop. So today I'm going to talk about the topological phase transition in population and mass imbalanced Fermi mixtures. So the outline of this talk is, outline is the first I'm going to talking about the topological phase transition and in the ultra-cold Fermi system, and then briefly review the equal mass fermions and then unequal mass Fermi mixtures, and briefly discuss about thermodynamic properties, how to probe the topological phase transition in these systems. So first, let me discuss on the topological phase. So S-wave Fermi superfluid in the 3D dimension turns out to be just a crossover. So in the weak interaction regime, the S-wave superfluid is just BCS type, and the chemical potential is close to Fermi energy, which is positive. And as we move on to the strong interaction regime, it's the BC type superfluid, with the chemical potential is just half of binding energy, which is negative. So during the BCS to BC evolution, the chemical potential is smoothly changing, and order parameter is smoothly changing, and there's no any change in the symmetry in the order parameter. So it's just a simple case of crossover. However, in the D-wave superfluid in the 2 dimensions, in the weak interaction limit, the chemical potential is positive, and in the strong interaction limit, chemical potential is negative. And during this, the BCS to BC evolution, there is no symmetry change in the order parameter. Still, in the BCS side, superfluid is the D wave, and in the BC type superfluid is also D wave superfluid. So there is no change in the order parameters. However, if you take a look at the structure of the excitation spectrums, in the BCS side, when the interaction is weak, there are 4 nodal points in the 0 energies. So it's a gapless D-wave superfluid. But in the strong interaction regime, the chemical potential is negative and opens the gap, and 2 excitation spectrum shows the gapped D-wave superfluid. So in this case, even though there's no symmetry change in the order parameter, but it's change in the topology of the 0 energy excitation, which called the nodes. So this kind of change in the topological property is called the topological phase transition. So BCS-BC evolution for D-wave in the 2-dimensional system shows the topological phase transitions. So there are more examples. So this is a S-wave superfluid in the presence of spin-orbit couplings. So if it's combined with the external Zeeman field, it also shows the topological transitions. So in this case, the control parameter is the external Zeeman field. When the Zeeman field is very high, the excitation spectrum shows it's a gapless gapless S-wave superfluid, and this red ring represents the nodes in the in the excitation spectrum. And as it's decreasing the Zeeman field, this ring shrinks to a single point, and when the external Zeeman field is very low, it's opened the gap, and this node vanishes, so it's in the gapped S-wave superfluid. So this is another example in the topological phase transition in ultra-cold Fermi system. So this topological phase transition is connected to the Lifshitz transitions, which is associated with the change in the topology of the Fermi surface. So this cartoon shows one of the example of the Lifshitz transitions in the non-interacting system. So in this case, we control the pressure. Then this Fermi surface, single Fermi surface, the neck is collapsing as we increase the pressure, and finally ends up with the 2 disconnected Fermi surface. So the topology of the Fermi surface is changing as controlling the pressure. So this is called the Lifshitz transition. So the topological phase transition is related to the Lifshitz transition in a sense, the change in the topological property in the momentum space. So now, then what will be the next? So this is the list what we are going to do and what we have done, and still in some of them is still in progress. So we're gonna have a further study of spin-orbit effects and maybe P-wave superfluids and the effects of disorder and multivariate effects, and maybe the effects of population and mass imbalance, the Fermi-Fermi mixture on the topological phase transitions. So today I just focused on the population and mass imbalance effects on the topological phase transition in the ultra-cold systems. So first, let me discuss on the equal mass fermions. So for the equal populations, for the S-wave superfluid in 3 dimensions in the homogeneous system, so we can write the Hamiltonian density with the kinetic energy and the interaction energies. So for the simplest case, we used just the parabolic dispersion for the single particle. And then the second term describing the interaction between the 2 different hyperfine states. So I'm going to call spin up, spin down in analogy with the 2 half spin electronic systems. So it's a 2-state system. And then interaction parameter G is associated with the S-wave scattering parameter derived by this just the standard scattering theory. And our strategy is to also calculate the gap over parameter equation with the constraint of conservation of total number of particles, and then looking for the solution, the self-consistent solutions of which are the chemical potential mu and the uniform superfluid order parameter delta. In the unequal population case, because the number of particles for spin up and spin down are different, so I'm going to define the population imbalance P as the number difference to the total number of particles, and corresponding chemical potential mu up and mu down will be different. So in the kinetic energy term, I include a chemical potential for the spin up and spin down to different hyperfine states. And the interaction in this model, just the interaction between the contact interaction between the 2 different hyperfine states, spin up and spin down. And then I'm going to solve the gap equation and number equation self-consistently to find the solutions, chemical potential and order parameters. And for convenience, I'm going to define the mu plus and minus in this way. Okay, so once I get all the solutions as a function of population imbalance or the interaction or the temperature, I can construct a whole phase diagrams. So first, let me show the phase diagram at 0 temperature in homogeneous strip in the population imbalanced and the interaction parameter space. So N is the label of the normal phase, and U is the uniform superfluid phase. So it's S-wave superfluid phase. And in this region, labeled by NU, is the region where the uniform superfluid phase is. Uniform superfluid is unstable. So there are many possibility in these regions, maybe phase separation and finite center of mass momentum pairing or super solid. But in this talk, I'm not going to tell more detail. I just focused on this uniform superfluid phases and regarding to the topological phase transitions. And then how we can say this uniform superfluid is stable. So to determine the stability of the uniform superfluid phase, we need to resort thermodynamic fundamental thermodynamic principles. Is the maximum of total entropy of the systems. So from this, we can get the 3 conditions. One is from the thermal fluctuation, positive specific heat, and the other one is from the fluctuation in the number of particles. So we define the partial derivative of chemical potential with respect to the number of particles, then positive determinant, and one of the diagonal element is positive is the second condition. And third condition is from the fluctuation of the volume of the system, which is isothermal compressibility, must be positive. So these three conditions must be satisfied in order to get a uniform superfluid phases. Okay, so let's take a look at the simple case. I already showed in the BCS-BC crossover for the S-wave superfluid in 3D dimension. So when the population is balanced, so P is 0, from the BCS to BC evolutions, it's just a crossover. So during the BCS evolution, it's a uniform superfluid phase, which means no symmetric change in autoparameter and no change in the topology of the nodes and the excitation spectrums. However, when the population is imbalanced, we can see the topological phase transitions. So I'm going to fix just one of the example for the interaction in the BC regimes. So when the population is 0 in the BC, the particle whole excitation spectrum shows it's in the fully gapped phases. However, when the population not 0, for example, is around 0.5, then quasi-whole excitation spectrum crosses the 0 of energy. So this blue dot is actually a surface of the sphere in 3 dimensions. So I'm going to call this US1 phase when the system is in the uniform superfluid phase with just a single surface of the 0 nodes. So in this regard, when the population is 0, P is 0, is called US0 because there's no nodes. Okay, so the US0 is fully gapped phase and US1 is the gapless phase. So there's a topological phase transition between the US1 and US0 phases because there is no symmetry breaking in the autoparameter, but there is a change in the topological structure of the nodes. So now there's another example in the unitarity. So this is the quasi-particle and quasi-whole excitation spectrum in the equal population case. So they are symmetric between they are particle-whole symmetric. But tuning the population balance, we can change the chemical potential, mu plus and minus. And by changing the chemical potential, we can shift the energy spectrum up and down. So maybe it's possible to get this fully gapped phases can be gapless phases by tuning the population imbalance. So I just pick up some points to showing the different topologically different phases. So when the population is very close to 0 at the point labeled by 1, if you see the excitation spectrum, this quasi-particle and whole excitation spectrum shows that it's fully gapped phases. So there is no nodes so it's called US0. But when the population is very large, but still is in the superfluid phase, it shows the quasi-whole excitation crossing the 0 of energy twice. So these 2 points forms in 3 dimensions. It forms a surface of 0 of excitation spectrums. So I'm going to call this US2 phases. So there's a topological phase transition from the low population to the high population. So in the unitarity regime at 0 temperature in the homogeneous system, there's a topological phase transition. But the issue is this topological phase transition is hidden by the non-uniform regions. So my argument is not applied in this region. But there is another direction. So we can control also temperature. So that now then, is there any topological phase transition in the finite temperatures. So let's look at the finite temperature at the unitarity regimes. So this is a phase diagrams at the unitarity as control the population imbalance. So these two dots indicating the boundary between the two different topological phase. Actually, at the zero temperature is hidden by the non-uniform regions. But as we increase the temperature, the uniform superfluid phase is stabilized, and also it shows some of the different topological phases. So fully gapped phases around the middle, and the US2 phases around. Okay, and so this red dots indicating the Lifshitz points, which is the multi-critical point surrounded by the normal and the uniform superfluid and non-uniform superfluid phases. So we have 4 Lifshitz points. Okay, so and this black line is showing the boundary between the two different topological phases, and this black line is indicating the second order phase transition from the superfluid to the normal phases. Okay, so then how can you prove the new class of phase transitions? So one way is to see the momentum distributions. So this is a momentum distribution at the unitarity in the US2 phase, and this one is US0 phase. At finite temperature is around 0.7. Normalized by the TC. But the problem is hard to see, the difference between US2 and US0 phases. However, it turns out the spectral function is very useful to see the difference between these two phases. So in the gapped phases, there is no peak in the spectral function at zero energies. However, in the US2 phase, spectral function shows the two significant peaks, so which corresponds to the position of radius and corresponds to the radius of the two surface of nodes. And then this one is indicating the boundary between the gapped and the gapless phases. Okay, so now then, how about unequal mass Fermi mixtures in the still can you see the topological transition in the unequal mass problem? Okay, so in the simple model, I'm going to use the single particle dispersion as a parabola. So blue one is for the light particle, and heavy one is the red one is the heavy particles, single particle dispersions, and I'm going to redefine the chemical potentials and Fermi momentums. And there are many theories that developed for these systems. Okay, so for the unequal mass Fermi mixture, we can write down the Hamiltonian density. So the kinetic energy term, including the mass difference between the light and heavy particle. So in this case, I am going to use the spin up, spin down for the notations. And the second term is describing the contact interaction between the two different species. One is the heavy and the other one is the light fermions. And then interaction parameter is associated with the S-wave scattering wave, and new defined mass M plus, which is defined as in this way. And also, the same strategy, I'm going to solve the order primary equation and now two different number equations, and then looking for the solution of chemical potential for the light particle and heavy particle and the uniform superfluid order parameters. Okay, so now then we can ask a question: how different is the phase diagram for population imbalance mixture of unequal mass fermions from the mixture of equal mass fermions? And is there a topological transition in this system? So let me answer the questions. So this is the zero temperature phase diagram at zero temperature. In the homogeneous system. So I just pick up one of the example for the Fermi-Fermi mixture is lithium potassium. So mass ratio is 0.15. So as we compared from the equal mass case, if the mixture by the same mass of Fermi-Fermi mixture looks symmetric between the positive and negative populations. But in the unequal mass mixtures, so when the light atoms in excess, the superfluid phase is more stabilized. So I'm sorry, it must be U and U. So non-uniform region gets smaller. However, when the heavy atoms in excess, the uniform superfluid is getting unstable. So the non-uniform region is expanded when the heavy atoms are in excess. So there are some the difference between the equal mass and the unequal mass mixtures. So now let's see if we can see any phase transition in the topological nature. So for now, just ignore this non-uniform regions. So this dotted line indicating the chemical potential plus, which is the average of chemical potential with spin up and spin down, is zero line. So when the system is in the left side, in the superfluid phase, the excitation spectrum shows there are two surface of nodes, two surface of sphere of nodes. So it's in the US2 phase. On the other hand, on the right side of this dot line, there is only one the surface of sphere of nodes. So it's in the US1 phase. So there is a phase, topologically, phase transitions across this mu plus is zero line when the light atom is in excess. And also, we can see this topological phase transition by probing the momentum distributions. So when it's in the US2 phase, so we can see the two discontinuity in the momentum space. And when it's in the US1 phase, it's only one discontinuity. So still we can see a difference between two phases. But however, this phase transition is hidden by the non-uniform phases. And also in the unitarity is just hidden by the non-uniform regions. However, we can turn the other direction, which is the finite temperature. So we control the temperature, then we see the uniform superfluid phase is stabilized. So we can see some uniform superfluid phase, and we see the many different topological phases. So the fully gapped US0 phase and US2 phase, as we already seen in the equal mass mixture. However, there are new gapless phases, which is US1 is emerging in the unitarity regimes. And we can see the difference of these topological phases as we see by probing the excitation spectrum. So fully gapped phase, which is US0, is the quasi-particle and whole excitation is fully gapped. There are no crossing of the zero energy. And the US1 phase, the quasi-particle excitation just crossed the zero of energy, and US2 is there are two crossings. So these topological phases classified by looking at the excitation spectrums. Okay, so now then what will be the phase transition between these topologically different phases? So I put just two phase diagram for the equal mass case and unequal mass case. So for the equal mass mixture, there's no topological phase transition when the population are balanced. So there is only the second order phase transition between the uniform superfluid to the normal phase. However, when the mass for the light and heavy particle are different, for example, the ratio is 0.15, there is a topological phase transition inside the uniform superfluid phase from the gap to the gapless, US0 to US1 topological phases. And also, when the population are imbalanced, there were the topological phase transition between the gap to gapless, which was US0 and US2 in the equal mass case. However, in the unequal mass mixture, the topological phase is much richer. So there are two topological phase transition between the gap to the gapless phase, and also new topological phase transition between the gapless, two different gapless phases, US2 and US1. So then how can you prove? Okay, so still, yeah, spectral function is useful in the unitarity at the finite temperature. So US1 phase, it shows the single peak, which corresponds to the single surface of a sphere of nodes. And then US0 is there's no peak at the zero energy, and US2 phase, there are two peaks. So by probing the spectroscopic property, we can see some topology of the system in the momentum space. But now then the question is that what about thermodynamic properties? So still, can you see the evidence of topological phase transitions? But it's hard. So so this is a plot of pressures as a function of population imbalance. So these black dots indicating that some second order phase transition between the uniform superfluid phase to the normal phase, and these two dots indicating the phase boundary between the two different topologically different phases, US0 and US2. However, so in the boundaries, the changes are very weak. So actually, it's hard to see the topological phase transition by probing the thermodynamic property. So, and also for the population unbalanced case, is hard. And then another quantity, I'm going to show the compressibility. So because it's the population imbalance system, we introduced a matrix of compressibility, which in this case alpha beta is index of the spin up and spin down. So still at the phase boundary, it's hard to see the topological phase transitions. However, this topological phase transition is associated with the change in the topology of the momentum in the momentum space without any breaking of the symmetry of the system. So maybe it will be possible to take a higher derivative of thermodynamic potential or with respect to the thermodynamic variable, then we may see some evidence of these phase transitions. So, for example, this compressibility is related to the second order derivative of thermodynamic potential with respect to the chemical potential. So, if we take the third order derivative, then we see some evidence. So, it may be called the third order phase transition, or if you need more, then maybe fourth order. And actually, it's still we are in progress, so we have some of the results regarding some higher order phase transition. So we have some small evidence for the third order phase transition by probing the thermodynamic properties. Okay, so here is my conclusions. So I discussed about a special class of phase transition, which are topological in nature. And it belongs to the Lifshitz class. So it can be occurred in various ultra-cold Fermi systems, particularly in mass and the population imbalanced mixture of fermions. Okay, thank you.
Time for some questions.
So this topological phase transition is really a phase transition at finite temperature, or does it become crossover?
It's a phase transition. It's a phase transition, yes. So in order to see the actually in order to see this phase transition, so we need to see some thermodynamic properties. So as I said, maybe for now, I cannot show the sharp evidence, but there is some evidence in the higher derivative in the thermodynamic potential. So it's in the third phase transitions, third order phase transition maybe. So it still is in the, it's not crossover.
Yeah, but actually, Yuzuki asked at finite temperature.
Yes, still is the finite
It is at
temperature.
finite temperature. Okay.
Yes, it's a,
Oh.
so this line indicating the phase transition, not
Okay,
crossover.
okay. My question actually is related with the Yuzuki. Apart from the numbers, okay, but if one would go beyond mean field, do you think that this topological transition will still exist? I wonder if the very existence of the topological transition is an artifact of mean field, which would not survive inclusion of fluctuations, or not. Not, of course, the overall phase diagram will change, but do you have any feeling about that?
I'm not so sure, but so even though we include the fluctuations, I think still, we can see it's the topological transition. Yes, as you said, maybe it will be a little different, but this is a three-dimensional system, so I think the fluctuation effect is not that strong to destroy it.
It relies on the fact that if fluctuations do not change the structure of the excitation spectrum, which is a big if, right, then this is preserved. But if they don't, then you're going to go into some kind of crossover kind of structure. So, two questions there. But it's a big if. The assumption is that when you do the fluctuations, you're still using perturbatively. So it preserves the structure, so therefore it's still there even if you there's a big questions.
It's not so much a question, but obviously you're in good control of the PT diagram at given polarization and or given ratio of masses.
Mhm.
Now, in fact, then it is a four-dimensional space of parameters, right? So I'm thinking, is it too difficult to trace out the whole line? Let's say we don't have four-dimensional abilities, right? But let's say you work at fixed polarization, can you not then trace out the phase diagram in 3D? It will be like in 3D, not flat, depending on the ratio of the masses. And do the same if you fix the ratio of the masses and trace out all polarizations. So
Yeah.
you will have lines in 3D and maybe, I'm really lost. It's too complicated even in mean field.
Yeah, so I just take one example, which is very popular in the Fermi-Fermi mixture. So still, I'm working on it. It's in progress. I have some, we can make a trace out for the different unequal mass ratio.